Thanks all for coming. And I guess for everyone watching this in the recording, thanks for watching as well. So today's paper is called Sanity Checks for Saliency Maps. It's a paper written in 2018 and submitted to NeurIPS, and I think it was accepted, NeurIPS 2018, by a bunch of folks. One of them you might have heard of, Ian Goodfellow, and this is another person that I've heard their name around this kind of topic a number of times. So I guess these are sort of big figureheads in this area. And so the basic area that this paper is about is saliency methods. And as a brief primer to what saliency methods are, here's another paper. And this paper describes a saliency method called CAM, or class activation mapping. And so to actually define what a saliency method is, basically here's a good visualization. If you have an input image and you had some sort of neural network, we would like to know, after passing the image through the network and getting some sort of output, we would like to know how or why the neural network produced that output. And it's not hard to think of why that would be important to know, especially in critical applications like autonomous driving, or maybe people using AI for things like, criminal justice or deciding who's going to get what loan, etc. Those have really big real-world consequences if things go disastrously wrong. And obviously, we would like to know why they went wrong when they do, so that hopefully we can, design better models that hopefully also don't sacrifice performance. So anyways, saliency methods are a way to do that, are a way to actually know or to visualize what a neural network is paying attention to in the input that led to the output it produced. And so in this example, it looks like we have someone brushing their teeth, and then in another image, we have two people brushing their teeth. And so the classification output, or at least the argmax of the classification output, is brushing teeth. And if you look at that neuron in the last layer of your neural network, and then you ask, okay, neural network, why was your activation so high that led you to produce brushing teeth as your argmax? Then you'll get something that looks like on the second row. And these are the saliency maps. And all a saliency map is it assigns very high values to pixels that are particularly important in producing that classification output. And so in this heat map, the color red corresponds to very high importance, very large values in the saliency map. And blue corresponds to the lowest values. And actually, I think they even correspond to negative values. Clearly in this example, it looks like it assigns a lot of very high value pixels in this region for brushing teeth around the toothbrush and the mouth, which makes sense. You would expect that some explanation for why it produced brushing teeth would assign important pixels in this region where they're actually brushing their teeth and not, for example, in the background. So that's very reasonable. And we see the same reasoning in the second image. So here it's a slightly more complicated image. We have two figures, but our saliency method is still able to assign important pixels to both people. And we see the red is mostly surrounded the toothbrush again.
Wait, Jason, could I ask something really quick?
Sure.
Yes. So are the saliency maps generated just from the gradient due to a single output neuron, or over the whole output?
Yeah. So typically we're only concerned about the neuron that has the highest activation, so the
Okay,
argmax neuron.
I see.
You could do it with respect to other neurons that are not the argmax, but it's sort of like, why would you, right? Like,
Yeah.
the classification output that we're really interested in is the highest one. So yeah. And I mean, they also give another example of some dudes cutting trees, and it looks like the salient parts are this guy's head, as well as what they're actually doing, which is, sawing down a tree. So that's basically a primer on these saliency methods. And it's worth to know also for the paper, and the paper will also go into this, that this is just one example of a method to produce a saliency map. There are actually a lot of methods out there, and each sort of have their pros and cons. As the paper will show, not all of them are particularly very effective for very interesting reasons. CAM is a method. It's actually a very popular method. I think this paper has like, let's see, yeah, 3,400 citations. So it's a very, very popular paper. A lot of people know about this method. So if you ever bump into people at, I don't know, a conference where people are talking about saliency methods, and you bring a CAM, they'll probably know what you're talking about if they're well versed in this area. But CAM is very limited. CAM only applies to architectures where you only have one fully connected layer after all your convolutional layers. And before this fully connected layer, you have a global average pooling layer. And all the global average pooling does is it takes as input the final convolutional layer filters. And along each filter, it basically just averages over the spatial resolution. So if you have 32 filters, global average pooling will transform this into 32 values, where each value is just the average over the filter. And so CAM requires this very specific architecture. And I think if you had an architecture that wasn't in that specific configuration, you could actually transform it into one. I think you could replace like a couple extra fully connected with just more convolutional layers, I think. Anyways, so yeah, that's kind of like a brief primer on one of the saliency methods. So back to our paper. So we talked about saliency methods. We looked at an example of one. We talked a little bit about why they're important. So, we had this ideal, we had this goal to understand what goes on behind the black box of neural networks. And over the years, people have developed a lot of these tools, these different saliency methods. And, we thought these were, our heroes, that these were going to save the day, that now we know everything that goes on inside the neural network. Now we've got perfect explanations, goodbye black box, we solved it, right? And then along came these people, and they showed through a really simple experiment that no, actually, some of these are pretty bad, or at least they don't give the kind of insight that we thought they did. And it's really embarrassing, I think, because the design of the experiments to show this result are very simple, like they're very easy to understand, and we'll go over these experiments and design of them. But the implications are very, I think, revealing, and shows that we still have a lot of work to do in this area. And so before we begin, I'll just start a poll. So here I have a very specially picked example that I actually came across during my research, and I was scratching my head at this for like a week. This is some stuff I got. So the Sanity checks paper, they released their code on GitHub, and they have, it's like really well written code. or at least to some extent, that you can run and basically reproduce all the results in paper. And so I basically ran this on their demo models and stuff, and tweaked some things and got some interesting results. This, by the way, is not directly related to my research. That is a secret, what I'm actually working on. But this is sort of something like anyone can run if they wanted to. But anyways, the question here is, we have this neural network, and we also have a test image. And we pass this test image through the neural network. And we get some classification output. And basically, we run one of our saliency methods, for example, ACM or whatnot. This one in particular is just gradient, which is just derivative of the output neuron with respect to the input image, which is probably like the simplest possible saliency method. So we have this gradient saliency method. And here I show a bunch of saliency maps, or possible saliency maps. These are all legitimate saliency maps. They were produced by doing something and running saliency method on them. But clearly they're different because what I did to get them was different. And so my question here is, which saliency map is most plausible, or I guess, in your opinion, is the best saliency map given this test image? And I guess I can start a poll. Let's see, launch polling. So let me know if you don't get the poll. Okay, I see 0 of 2 voted.
Wait, Jason, it says to respond to grayscale and color.
Oh, just respond to grayscale and put whatever for color. We'll do the color one next, but right now we're just doing grayscale. Okay, so it looks like everyone answered. So here are the results. And as you can see, most people think B. In fact, everyone here thinks B. And I'm sorry to say that B is not the right answer. So there's a mystery here, and we'll dive deeper into the mystery. But let's go through our options and let's kind of evaluate, each one on their own. So I'll start actually with option C, probably the worst looking option. Actually, I'll just kind of make remarks. I won't say which one is the right one yet. But C, it looks to me as if C is just some sort of random noise here. And so it doesn't seem like there's much important information we can extract out of this saliency map. Option D, it looks like it has more shape, but it doesn't really look like the same shape as the input image. In fact, it looks like the number 7. It doesn't even look like a 1. And so that leaves option A and B, which are the ones that look the most similar to the input image. So that's probably closer to what we want to see. And now the question is, well, assuming that it's either A or B, how can we tell which one is the right one? And I'm actually going to also say that this is a little bit of a trick question, because one of these maps is produced by a fully trained neural network that gives like 99% accuracy on your test set. And the other map is produced by a neural network that has not been trained at all. The weights are totally random. It's giving you garbage results, but we get something that's still shaped like a 1. And so that's the mystery, why this happens. And what you'll see is that if you also treat your tools to produce your saliency map also as a black box, and not really think about how do they work internally, you can get very misleading results, right? I mentioned that one of these is on a neural network that has not been trained at all, yet we see 2 cases where they look like they have the same shape. And so someone could be very easily misled and say, oh, my neural network is perfectly trained, right? When in reality, it's actually probably the world's dumbest neural network. And so here on the second slide, I showed the same maps, but the difference between these two is that in the first one, I took the saliency values and just absolute valued them. So this is just the magnitude of all the saliency values, and that produces a grayscale saliency map. Here we show a little bit more information. I don't take the absolute value of everything and instead just show the raw positive and negative values. And so I guess I won't relaunch the poll because I sort of explained a lot already. You know, in this case, red corresponds to positive, blue corresponds to negative, and white is just 0. And I mean, we see the same shape. We start to see, well, you know, if you look at this, it looks pretty much like this, except just confined to the region with 1. And this sort of looks like this, except it's like maybe a little bit more of a different shape, right? So at this point, I still haven't told you what the correct one is, but maybe you're starting to form your own opinion. And so I actually won't get into the reason or which one is the correct one yet. I'll first go through the paper, and at the end of the session, we'll solve the mystery, and I'll explain why these results are the way they are. That was a fun little exercise to show how these sort of saliency methods can actually be very dangerous. You know, we can't just automatically assume what goes on within the black box of the neural network by just looking at the saliency map alone, which ironically was the purpose of inventing these saliency methods in the first place. So clearly there's something a little bit hand-wavy here. And so these people were also very concerned about how well do these saliency methods actually tell what's going on inside the neural network, right? You know, I mean, again, like the simplest possible saliency method is just what we call the gradient or vanilla backprop saliency method. And all it is literally, again, the derivative of the output with respect to the input. And I mean, intuitively, this makes a ton of sense because the derivative is, I mean, you can think of it as a measure of importance, right? You can think of it as like, you know, pixels with high value for the derivative are the ones where you only need to change them a very small amount to get the biggest change in the output, right? And so these must be very important pixels. And that's, you know, what people think is why a gradient method makes a lot of sense for as a saliency method, right? But it's not perfect. And I mean, if it was, then we wouldn't have, you know, explosion of so many different saliency methods. We'll see why. We'll see why some of these other ones are not very good either. So so these people designed a few experiments to demonstrate what can go wrong in these Saliency methods. Before getting into the experiments, it's worth sort of talking about what even is a good saliency map, right? Let me see if I could find a section where they talk about their criteria. Let's see. Okay, well, they don't talk about it in any section, but I'll just mention it now. So the first thing we would like to make sure, like the first criteria for a good saliency method, actually not just a map, but a method itself, is that the saliency method should be faithful to the actual model, right? And I mean, that makes sense. And it's probably something you're wondering, like, well, that's so obvious. Are there methods that aren't faithful, right? Like that are giving these garbage, maps that don't even have anything to do with the neural network? And the answer is yes, that the experiments will show. But then the next question is, well, how do we test for faithfulness to the model, right? And by the way, faithfulness, what it means is if I have a neural network that was perfectly trained, it's like 100% accuracy on the test set. And then I have another neural network that was not trained at all and produces garbage results on your test set, sort of similar to what we saw in the contrived example. Hint, hint. If we have these two different models, we would hope that our saliency method, if we ask it, hey, can you explain this particular output on both of these networks? We would hope that the answer is very, very different between the two, right? We would hope that on the perfectly trained model, our saliency method would be sensible, would make sense. It would look somewhat like the input, or at least, features of the input that are very reasonable. And we would hope that on the garbage neural network, you would get a garbage saliency map, right? You would get a garbage explanation of why we produced a garbage classification output. That is our hope. That is our criteria. And so to actually test this, the authors designed this experiment called the randomization experiment. And so I'm going to go to the section that they talk about this. Yeah, so here, let's see if I can find it. Yes, this is a good example. So there's a few different ways you can design. Okay, actually, I'll first introduce what a randomization experiment is. So we introduced criteria of faithfulness to the model. How do we test this? Well, what we can do is we can sort of randomize a subset of the neural network's weights, right? And I mean, we could do this in a specific order, maybe like by successive layers. Maybe we could just, randomize like the middle of the neural network. Maybe we just randomize the entire network. That would correspond to an untrained neural network. Or, conversely, not randomize anything is a perfectly trained, hopefully. But starting with a perfectly trained and then randomizing certain weights, we repeatedly test what does our saliency map look like. And so here in this image, in this diagram, they basically sum up the entire experiment. And so along the vertical axis, there's all these different kinds of saliency methods. And you'll see that the very first one was the most simplest method that I mentioned earlier, gradient, right? This is the gradient of the output with respect to the input. Here you'll note grad cam, and cam is the same cam that we saw in the other paper. I think the same authors did a follow-up paper where they produced a more general version of cam that wasn't restricted to that very particular architecture, and they called it GradCam. I think it was the same authors. And you also see there's a guided GradCam. So you see like there's different variations of, these different saliency methods. And each kind of, you can see like visually, each are sort of giving different importance values to different pixels in different ways. And so along the horizontal axis is we have our different layers of the neural network. So this is a pretty deep neural network, or well, not too deep. I would say maybe like a medium-sized neural network. Although neural networks are getting pretty large these days, so maybe this is even just as small by that standard. But this is on ImageNet apparently, and the leftmost column corresponds to your output layer, so your logits. And as you go to the right, you go earlier and earlier into the network. So by the time you hit this side, you're already in the convolutional layers, and you're pretty much at like the very first layer. So it's kind of like your neural network flipped, right? We start from the output, and then we go backwards to our input. And in this experiment, they called it the cascading randomization experiment. Cascading because we're randomizing our weights layer by layer successfully. But each time you randomize, we keep the randomization of the previous layers. So what you're seeing here is these saliency maps on a neural network whose weights starting from the logits layer up to whatever column of the neural network, inclusive, is randomized, right? So for example, if we look at this column, right, this is like what, the 7th fully connected layer of the neural network, if that's even fully connected. Mixed, I don't know what mixed is. Assume mixed is fully connected. So this is like what, the 7th fully connected. So what that means is that your logits layer, your 10th, 9th, 8th, and 7th layers, the weights for those layers are all randomized, right, up to that layer inclusive. So that's kind of what the randomization test is doing. And so you could think that your extremes here, here's the original saliency map. And here corresponds to other extremes where you've basically randomized every single layer in your neural network. And so this column corresponds to a completely garbage neural network, produces completely garbage output, because all your weights in the entire network are randomized. It's as if your network was never trained at all, right? And in the, here's another hint to the mystery. In these, the code they provide in for this paper, when they randomize the weights, all they do is call the initializer. So this whole thing is in TensorFlow. All they do is they call the initializer for that layer's weights. So basically it just reinitializes, using whatever initialization method was defined when the model was defined. It doesn't truly randomize. It's just the randomization depends on how the model is defined in their specific code. And we will see that actually that's a pretty important part to our mystery. Anyways, so as you can see, I mean, as we randomize more and more of our neural network weights, we would hope that, even after the first layer of randomization, we would get garbage results, right? Because if that wasn't the case, if we randomized only the logits layer and our saliency map didn't change that much, then that probably means that that layer is not very important, right? Like we would probably just do without that layer in terms of getting our saliency map, right? So in a way, it's sort of like a ablation study on the importance of each of the layers. And so we would also hope to see if as you randomize more and more layers, that this sort of gets worse and worse. You know, we would see, you know, if it wasn't the case that the first layer did it, then it's got to be, you know, at some point, right, we would start seeing pretty terrible saliency maps, right? And if you look at it, well, it's not exactly what happens for some of these methods, right? So for example, the most obvious striking one to me is guided backprop, right? Which is sort of like a modified version of gradient. And in guided backprop, you know, okay, so here's our original saliency map. Here's what it looks like when we randomize the lodges layer. It looks pretty much the same, right? Like I can't even, I mean, if you zoom in, like I can barely tell that there's a difference between these two maps. And that actually remains true even as you randomize more and more of the neural network, right? Until you get maybe to about here, you start seeing more noise in this area. You also don't see these corners anymore. Okay. Finally, we start to see the bird is getting a little bit more noisy. So maybe we're doing something right now. But I mean, even in the case where you have a totally randomized neural network, we still see the shape of the bird, right? And I mean, if you compare this to the original map, you still have a lot of that information in there, right? And it didn't matter whether or not the neural network was fully trained or totally randomized as if it was never trained. The maps look super similar, right? And so that's bad. That's not what we want to see, right? We want to see sensitivity to the model weights, right? We want to see this totally garbage, right? Because that's the only thing that makes sense, right? I mean, you kind of see this for, if you just look at this entire row, right, corresponding to totally randomized neural networks across all these different methods, we kind of still see the input in pretty much all of these methods, right? If you look at the layer before, for example, in gradient, it's as if the input disappears just for a little while and then reappears here. And so we'll actually talk about that phenomenon. It is connected to our mystery that we went over earlier. I mean, if you had to pick something that was the most faithful to your model in this case, just looking at these results, you'd probably pick maybe smooth grad, because I mean, clearly there's a portion of the neural network for which if you randomized it, you would get the garbage results that you're seeing. Again, for some reason, the input reappears at the final as you totally randomize network, but we'll kind of go over a related example and why that happens. And so, you know, I mean, it's not perfect, clearly. Like, you could basically not randomize like more than half of it and still get these good results. So that is pretty much just one example they found. And I mean, there's a whole bunch of other examples on this cascading randomization test. And I think they put it in there. Yeah, so here's another example on just some other images. And they do it for one specific saliency method. And I mean, over and over again, like, this is not, you know, that test image that they showed in the previous example wasn't a contrived example that just happened to work, that just happened to fool all these methods, right? This is happening across all these different test images. So that's telling us that it's probably, I mean, it's not the image fault. It's not the, I mean, it's probably not the neural network architecture fault. Probably has nothing to do with the neural network weights. It probably has everything to do with how the saliency method was designed, right? Clearly this is very disheartening, I think, to a lot of people who had hoped that these methods were the answer to understanding the black box mystery of neural networks, right? We thought we had solved it, but this very simple experiment had kind of destroyed all those hopes. Let's see if there's some other examples. Different visualization scheme. Here's a bird example. And then you also note that, I mean, GradCam, it looks pretty okay. I mean, like, we see garbage maps pretty early on. But clearly for the other ones, this is not the case. So it looks like they do more. There's dogs, and yeah, let's see. Is there anything that's not? See if I can find a different data set. We did. Oh, here's fashion and mist. So this is not just particular to the data set. This phenomenon happens across pretty much anything that you throw at it, which gives further evidence that it's the method's fault, not anything else. Although here we see something interesting. I mean, it looks like, you know, the saliency map does kind of explode into totally randomness, which is kind of what we want to see. So, and another thing you'll note is that this is a much narrower network than ImageNet, right? Or Inception version 3. This is like a very tiny neural network, right? It only has like 4 layers, right? And so maybe it also has something to do with how deep your neural network is, how complex your model is, or how many layers you have, right? And so that's another observation. And here's another example from fashion and mist. I mean, we see retention of, you know, the original image, and here's normal mist, which is the image you saw in the mystery example that I gave. So yeah, I mean, you see, like, it's as if the shape never changed, and, you know, it's like, it looks like the end of the world for all of these poor saliency methods. They got obliterated through this very simple randomization experiment. Blah blah blah. So there's a bunch of other ones. And so, you know, that was just one example of an experiment that can show these methods aren't that great. But as if that wasn't hurtful enough for these saliency methods, the authors also produced another experiment that showed a different angle at why these aren't good. And I'm only going to briefly touch on that the other one. The other one is the data randomization test. In the data randomization test, instead of randomizing your neural network weights, we leave those fixed at your perfect, or sorry, forget what I said. So instead of randomizing the neural network weights, what we do is we randomize the data set labels, right? So, and then we train the neural network on them, on these garbage labels, right? So now you have your data set is garbage, right? And we would hope to see that if our data set is garbage, then, I mean, whatever our neural network, probably, one, it should be garbage as well. And two, our salience methods, therefore, should also be pretty garbage, right? Because you just don't have any more class consistency. This is like totally randomizing all the labels like independently for each image, right? So it's not like all the 7s became 2s. It's not like a simple substitution, right? It's actually literally total randomization on the test data set. Sorry, the training data set. And you would hope to see that, again, everything is garbage, right? If you see things that look sensible in this case, that should not make sense, right? That should be very suspicious, right? Why would anything look sensible in this scenario? And I don't, let's see, true labels, yeah, here. So here's an example of, in the first column corresponds to the neural network where it's trained on the correct labels, right? So these look reasonable, nothing fishy there. And in our second row, we have the neural network that's trained on the totally random labels. And what we'd hope to see in the second row is that everything's different. Everything looks garbage. But that's not the case in some of these methods, right? In a few of these methods, that looks like to be the case, right? Like, for example, gradient and smooth grad, again, look like they're pretty faithful to the data. But all these other methods don't look like, I mean, even GradCam, you could sort of still see the zero shape in the saliency map. It's a little bit messed up, but you can sort of still see a shape. And here you can clearly still see a shape, especially in guided to GradCam. Wow, that looks, even the colors are the same. All right. Here you see the colors are a little bit randomized, but still the shape overall. And by the way, this is also related to our mystery. So this is really bad, right? You know, in our previous cascading randomization example, we showed that these methods are not faithful. I mean, not faithful to our model in you know, certain examples that we've shown. And in here, we're showing that it's not even faithful to your data set. If you totally randomize your label and you train your neural network on it, you'll get clearly the same result as if you had done the correct training set labels. So it's as if it's not even paying attention to, one, what your model weights are, and two, what your training data set was. And so, like, what even is it paying attention to? Like, what is our saliency method actually telling us, right? If it's not either of those things. The hypothesis that the authors give, let me show you the image. Let's see, is in this diagram. So hopefully you're all familiar with edge detection. If you're not, basically it's you're looking for a certain feature, which is called an edge, which is literally what it sounds like. It's just an edge in your image. And you basically run that over your entire image, and you basically get another image where all those edges are highlighted, right? And so that's what we get in this rightmost column here. They just ran like a simple edge detection algorithm on your input image. And what the point here that they're trying to make is that, gee, a lot of these saliency methods look pretty similar to our edge detector simple algorithm, right? And our edge detector is an example of, by construction, a terrible saliency method. Because one, edge detection, it doesn't care so much that, you know, what your weights are, right? It only cares about your input image, right? It doesn't care that there's a neural network there. All it needs is just your image, and it can give you your edge detection, right? So it's not faithful to any model. It also doesn't care that you had a training data set, right? Because again, it doesn't care that you had a neural network. So it's also not faithful to a training data set. And so by construction, edge detection should be the worst possible kind of saliency method that you can ever come up with. Yet the results that it produces are remarkably similar to what we're seeing with saliency methods that were constructed with the intention of hopefully being faithful to both model and data set. And so the point they're trying to make is, well, it's probably not, right? Like, these saliency methods are probably nothing more than just fancy edge detection. That it's this really crushing blow to a lot of these people's research over a very simple experiments that honestly I think anyone could design. Like, these, it doesn't take a genius to come up with these experiments, even though these authors are very, very, very smart and accomplished. No, this is like a total absolute blow, I think. So, you know, if our saliency methods that people have spent so long and so much effort in developing, and 3,400 citations and so on. If they're nothing more than just fancy edge detectors, then what's the use of them? Do we have any hope in understanding what goes on inside a neural network and explaining the black box? That's kind of a open question. I don't have the answer to that. And part of it is, I think, because, these saliency, like, what even is a good saliency map is super subjective, right? Like, if you showed a saliency map to one person and showed it to another person, right? Maybe the wisdom of the crowd would eventually converge on an answer, but there's still some variation, right? It's still a bit subjective, right? Clearly from the example I showed you, a very contrived example, the wisdom of the crowd wasn't even right, right? One, the problem is these things are very subjective, right? We're just visualizing a map and we're saying, oh, how good is it, right? That's not very quantitative, right? That's very qualitative. And so there's a lot of room for very hand waviness here. And so that's a big problem that that exists with these methods, I think. And so now we're ready to go back and explain our mystery. So let's see. Let's go to this slide. Actually, before I do that, by the way, this is the code for the paper, and this is just a notebook they provided. And I just ran this notebook before this this reading group session. And so I want to show you this example. And here you'll see that, hey, these look kind of similar, right, to what was in our contrived example here. And yeah, this is actually exactly where I got it from. These correspond to the opposite ends of the randomization experiment. And so hopefully you see your fallacy here, that you selected the saliency map that corresponded to a neural network that was entirely randomized, that it was as if it was never trained at all. And this, I think, is a good example of why we need to be very careful about just blindly trusting these saliency methods. I could imagine in the future, maybe someone has a job of, like, I don't know, investigating other companies' neural networks and trying to make, see how safe and reliable they are, right? And this, maybe a rookie signs up for the job and all they know is that, oh, I have a bunch of saliency method tools, right? Like I could just, use them on these images. And then, maybe they use them on some garbage neural network and they get something that looks like this and they're like, aha, it's perfect, and they report back to the company, everything's a-okay, right? Well, that rookie would probably be fired, sadly. But hopefully by then, when those kinds of jobs are common, we wouldn't have these kind of problems anymore. Hopefully we would solve saliency. So there's one last mystery, and it's why this happens, right? Like it looks like as we randomize more and more of the network, it does kind of explode, at least for gradients, it does kind of explode into randomness, right? A random salience map. But then immediately, once we randomize the entire network, we recover, it's like we recover the original input image, right? Like it suddenly collapses back to the input image, which is so strange. And I was actually stumped on this for a while, for like a week. And then I remembered an imaginary Gary Cottrell's voice kind of spoke into my ear. He said, remember the backprop equations. And I was like, oh, you're right. And so this is aside from Cottrell's 151B slides. I just copy pasted. And here we just have the equations for backprop, right? And again, this layer or this row, the saliency method is very simple, just gradient, right? The derivative of the output or gradient of the output with respect to the input image, right? It's so I mean in normal backprop you do it with you have the derivative of your loss with respect to your weights, right? But really, I mean the form is the same, right? You're just changing like I think at the output layer instead of the z, I think it's like w, because now you're taking with respect to the image. So this would be w instead of z. I think that makes sense. And so the problem here, if you remember your backprop equations, and by the way, this network has ReLU activations. And the one other thing that I didn't tell you is that the initialization method for the biases of this neural network just initializes them all to 0. And so you might start to realize why this is a problem if you look at the backprop equations. If you have an input image where this region, everything that is not the 1 is a 0 in your input image. And I mean, in this case, you have totally random weights, so it doesn't matter what they are. But whatever they are, multiplied by 0, you'll get an output of 0. If you add in bias to that is also 0, you'll still get 0. And then if you pass that into the derivative of the ReLU, right? I mean, that's a piecewise function, but apparently in TensorFlow, they define it as 0 for less than or equal to 0, and 1 for everything else. If you pass that to this portion, this will also become 0. And so that'll 0 everything else, right? In your giant backprop equation. And so that's exactly why we sort of recovered the input image. It's because of this very, very contrived example where we initialize their biases to 0. And that mathematically fooled us into thinking that, whoa, there's some kind of saliency going on here, right? When really it's just an artifact of the backprop equations. And by the way, the reason why it doesn't happen here is because this method smooth grad, it adds a little, it's basically the same as gradient. It just adds a little bit of noise to the input image. And so if you add a little bit of noise to the input image, all these zeros become non-zero and you don't have that problem anymore, right? And so that's why we see randomness, but not in this case, right? Even if the biases in both cases were initialized to 0. So more of the story is remember your backprop equations. It's kind of like eating your vegetables. Always remember your math of your basic math for ML. So looks like we're out of time, but I guess any of you all have any questions?
Yeah, so like after the paper got published about like how those saliency methods have been like they're basically useless. Like has there been any like new like saliency methods already or still under development?
That's a good question. I'm not sure about the saliency methods, but in terms of the goal of explaining neural networks or interpreting them and their decisions, there's another sort of angle that you can come at this, and that's so you'll notice that the thing that is similar for all these methods is that it requires sort of an already trained neural network as sort of a black box. And then you come in and say, okay, let's kind of probe this black box, right? And then you get a map, right? The other way that you can approach this is by construction, construct a model that is inherently interpretable. So you don't need this post hoc method of jabbing at the black box after the fact. You can actually just say, oh, our model is interpretable to begin with. Now we just ask it to interpret its results, right? And along those lines, yeah, there has been like more work in that area. For example, there's been work out of MIT that I'm particularly interested in for my research called self-explaining neural networks. And those are an attempt at a by-construction interpretable method for this.
That's pretty cool.
Cool. Oh, by the way, I'm sorry, Edward, I didn't see your questions. I didn't see them pop up on my screen, but is this kind of related to safety? Where did you ask that question again? Is this kind of related to safety? I mean, like this, yeah. Like, I mean, this research, yeah, it definitely is. Like, I mean, the whole fact, like, saliency methods themselves were invented because people were concerned about safety, right? Like, we wanted to explain what goes on in the black box in order to be safe and to have a level of trust in our models. But I mean, if we can't even do that with reliable tools that are trustworthy, then that's like a double problem, like a double untrustworthy problem. So yeah, it is definitely very, very related to safety. That's like our whole motivation.
Do you think like another way that I guess saliency could be like tackled is by like modifying the inputs, like basically adversarial examples?
Yeah, so could you give an example of what you would mean?
Yes, I guess like you would have like some image, I guess, and then you would basically like modify it in certain like do you like test out a bunch of different modifications, like maybe like occlusion and like other changes to the image, and then see how the network's output reacts to them?
Yeah, so there is an occlusion-based method where basically you have this like patch, for example, like a full gray patch, or doesn't really matter what color it is.
Yeah,
But you basically like just modify your image and put this patch over a region of your image, and you sort of slide this patch around. And the regions where the output changes significantly, where that patch is, are regarded as very important regions for your output.
I see.
The problem with that, I think, is efficiency, because obviously for one image, you have this patch that you're moving over and you have to reevaluate and you'll never go multiple times. I think another problem, I mean, well, maybe it's not a problem, is that this process is not differentiable. Because, I mean, I'm not even sure how you would, like, it's not defined as, like, for example, with gradient, right? That's basically just taking the gradient, but I think that's also itself a differentiable function. I'm not sure if it's too much of a problem, but I think that's another observation. So yeah, yeah, you could do something like that. People have done that. I'm not sure. I don't think people have done like a similar, like they've run these experiments I showed today on like occlusion based methods, but that would be interesting to test out and see if it passes these tests or not.
Yeah.
Yeah.
Interesting.
Cool.
Good stuff.
Great. I guess that's all, and I can stop sharing. And
Cool.
yeah, thanks for coming.
Yeah, that was a nice presentation.
Yeah, thanks.
Cool. All right. I'll see you later.
All right, see ya.